They're rarely seen because they happen so far above the Earth.
Moving on now to lightning, and of course lightning is what makes a thunderstorm a thunderstorm. Lightning is a discharge of electricity in or from a mature thunderstorm. Now, it has to be a mature thunderstorm because it has to have the height to get this charge separation, and it has to have the height for the charge separation to be able to occur. The charge separation occurs basically as ice becomes electrically charged, either positively or negatively, and sometimes water droplets, but it really takes the ice to do that. So one of the things needed for lightning is for there to be some ice. Now, mid-latitude storms, anything Florida or north, definitely going to have ice in it. But some of our storms in the tropics, they'll be a little rumbly, but they won't have significant lightning. And then oftentimes, tropical cyclones and the storms associated with that won't have a lot of lightning with them either, because essentially the storms are so warm there's just not a lot of ice. So you have to have a mature thunderstorm, and that lightning occurs when there is an electrical charge separation, known as an electrical potential, that becomes strong enough that it can overcome the insulating properties of air. So insulation just means electricity can't or has a very difficult time passing through the insulating body. So we know that copper wires are wrapped in rubber. Rubber is the insulator. The bigger and stronger the wire, the thicker the insulation is going to be. Enough electricity, it can move through that rubber, but it's a great insulator. Wood is a great insulator. Enough electricity, it can also move through that. Electricity can move through water. It can move through the ground. It certainly can move through metal very easily because electrons move very easily. But air is a good insulator. And so it takes a lot of electrical charge to overcome the insulating properties of air. When there's enough electrical potential, difference between positive and negative, then there is a connection between the two, and there's a discharge, and that discharge is the lightning stroke. So the charge separation, or the electrification of clouds, occurs when larger negatively charged particles fall to the base of the cloud, and smaller positively charged particles are lifted to the top of the cloud by the updrafts. There is a net transfer of positive ions from warmer, heavier objects to the colder and lighter objects. So positive ions, by bumping into one another, by colliding with one another in the up and the down drafts as these objects move by each other, positive ions move from the heavier, warmer objects to the colder, lighter objects, and you get generally a positive charge at the top of the cloud and a negative charge at the bottom of the cloud. And for most lightning strikes, about 80%, the lightning discharge happens either within the cloud or between two clouds that are next to each other as this charge separation occurs. The cloud-to-ground lightning occurs when the negatively charged base of the cloud literally induces a positive charge in the objects below, meaning positively charged ions are literally pulled up to the top of the objects because of the negative charge of the base of the cloud. And then you can see in this illustration there's a charge separation between the base of the cloud and the object below. So the charge separation between the cloud base and objects in the ground develops as negatively charged cloud base induces a positive charge at the surface because, again, opposites attract. Here is an illustration of that electrification of clouds where the warmer, heavier hailstone gives up some of its positive ions as it connects with that smaller, colder ice crystal. And the smaller, colder ice crystal becomes positively charged and goes up, and the hailstone becomes negatively charged and falls to the surface. So ice, as I said, is generally required for the electrification of clouds. So the lightning stroke itself is a fairly complicated thing, and it's something we see very, very regularly, and it happens very, very quickly, and huge discharge of electricity and heat. What happens in cloud-to-ground lightning, which is about 20% of lightning, it begins when the charge separation between the Earth and the base of the cloud is great enough that it causes a channel of negatively charged electrons, known as a stepped leader, to move toward the ground. So A, you've got your step leader. You don't see this. It's a channel of negatively charged electrons reaching toward the ground. And the reason why lightning is forked and it looks so tortuous is because it doesn't know where it's going. It's just reaching out for that positive, and it sort of darts back and forth. As it approaches the ground, a similar positively charged channel begins to climb toward the step leader, and that's coming up from the object on the ground. When the two connect, the positive current rushes back up the step leader, and the luminous return stroke is what we see. So again, the charge potential is highest where it's positive, so the positive goes towards the negative, and that's what lights up the lightning channel, and that's what you see. So if you've ever heard lightning goes from the ground up, the positive ions go from the ground up, and that's what you see. Why you see it stretching down is kind of a trick of our eyes, but the step leader draws down, the return stroke illuminates, and it goes up. And the return stroke instantaneously heats the surrounding air to 30,000 degrees Celsius, about 54,000 degrees Fahrenheit, and that creates the shock wave that we hear as thunder. So this animation is going to show us the development of a typical thunderstorm. Here is the updraft, and that updraft along with the downdraft of the rain allows for the electrical charge separation and the electrification of the cloud. Negative charge at the base of the cloud induces a positive charge on the objects below. A step leader reaches out toward those objects, and when the step leader gets close enough to those positive charges at the surface, and then the step leader connects and the return stroke occurs, and then the cloud kind of goes and dissipates its charge separation and continues to move on, and additional charge separations may form, which may allow for intra-cloud charges or lightning strokes, or maybe more cloud-to-ground lightning strokes. A little bit more detail that also gives us an indication of why we get the flashing or the multiple lightning strikes, because the first return stroke helps to equalize the charge separation, but sometimes it requires several to totally dispel the charge separation. So read through this, pretty good little illustration of how the lightning stroke occurs as well. Different types of lightning. You may have heard of forked lightning, ribbon, bead lightning, ball lightning, sheet lightning. By the way, ball lightning is oftentimes what they call St. Elmo's fire. Sheet lightning is basically intra-cloud lightning. And the concept of heat lightning is basically thunderstorms way off on the horizon that folks at one time saw often in the heat of summer. They saw the lightning, but they didn't hear the thunder, and they referred to that as heat lightning. So heat lightning is just any old form of lightning that somebody sees, but they actually can't hear. And again, different types of lightning. We have the cloud-to-ground lightning. We have the intra-cloud lightning, cloud-to-cloud lightning. And the last thing I wanted to point out to you is this lightning that reaches out from the side of the clouds or sometimes the top of the clouds. And because if they come from the top of the clouds, it's actually a positive strike coming down, that we are talking about what's known as bolts from the blue. And these are capable of traveling, in some cases, upwards of 30 miles away from the base of the thunderstorm. And this is the reason why, if you're at New Smyrna Beach and there's thunderstorms well inland and they're ugly and they're stormy and you think, well, the sky's blue over me, we're okay. Even in that situation, a bolt from the blue is not impossible, and lightning strikes can occur. And again, lightning strike heats the channel of air around it up to about 50,000 degrees Fahrenheit, about 5 times the heat of the surface of the sun. So certainly not something to play with. We will wrap up this lecture with just a quick peek at thunder, and then of course our next lecture, lecture 11, is going to be looking at hurricanes, tropical cyclones, and so that will be an interesting one. Thunder is the booming sound wave caused by the explosive expansion of heat as lightning heats the column of air around it to more than 54,000 degrees Fahrenheit. It takes about 5 seconds for the sound of thunder to travel 1 mile from the lightning strike. If the sound waves from the lower part of the stroke reach an observer before the waves from the upper part of the stroke, then you start to get that rumble of thunder. And also it takes lightning being quite a distance away to get a rumble. The rumble also occurs because the sound wave may have ricocheted off of buildings or mountains or trees or even other clouds. And so when you're very, very close to a lightning strike, you tend to get a clap, very, very high-pitched clap and a bang. Whereas if you're very, very far away from thunder, it'll be much, much more rumbly and last much longer. In some cases, those sound waves strike the ground and bend upwards, so observers at a certain distance from thunderstorms sometimes can't even hear the thunderstorms. So again, this wraps up our lecture on thunderstorms. Next is going to be tropical cyclones, hurricanes, tropical storms, and tropical depressions. So we will see you next time for Chapter 11, from Introduction to Meteorology, Tropical Cyclones.